shall now go through the process of setting up Gschem for schematic capture. We saw that the CIR file was refactored into the CIR file itself and the netlist file and the subcircuit file. The netlist file can in fact be generated through a schematic capture. So we will use Gschem to do the schematic capture, and for that we will install GEDA, sudo dnf install GEDA. This is what we will type. I have pre-typed the instructions for installing Gschem, and you can follow that. It will also be available in the resource. So after installing GEDA, in my machine it's already installed, you need to configure it in this fashion, one by one. Run gnetlist once, gnetlist, as given, indicated in the file alongside. You need to type in that. So that's it. Next we create a GAF directory. Make directory GAF, and also direct any errors. Done. See that the GAF directory has been created. And then going next, create a directory that will contain all the symbols. So we need to have this directory within GAF. So what I will do, I will copy and paste the symbols later. Right now I will just make an empty directory in GAF called symbols. I have made a list of symbols, a collection of symbols which you can utilize. I will share them with you, and we will download that from the website, and you can place it in the symbols folder. So in the symbols folder that will get created. If you run Gschem now from the command line, for example gchem from the command line, you will see that the schematic editor comes up, but it has a background which is dark. It's a dark background with white foreground. This is actually not good, in the sense that if you want to do documentation, you want to copy the circuit schematics onto your other documents, then you will have a black background, and in case you need to do some printing, it will be a waste of ink. So therefore it is always good to have the background as white, foreground as black. So to do that, we will use this portion of instructions to change the background color from dark BG to light BG. So this is what will happen. So let me do that here for you. So I will copy this portion and paste it here. So it will load into .geda Gschem RC in this command line where the background color is made light. So that's it. Now again, if you execute Gschem, I'll execute it from the command line here. So you see that the background is light BG, and the foreground will be black in color. So this is fine. We will use this syntax. Next, we need to configure that GEDA, the Gschem, finds all its symbols from a particular directory. And we have created a directory here, a GAF directory, and within GAF directory, a symbols directory. Within the symbols directory, you will be placing all symbols. These symbols need to be in the path, and therefore the component library search, whenever GEDA does the component library search, it has to look for in the user root GAF symbols, and this is the path that has to be included in the GAF RC file. So I will copy that here and execute. So it will get written into the .geda GAF RC file. Execute that. Now that is executed and you are ready to go. You are now ready to use Gschem. Let us now walk through the process of building a circuit schematic using Gschem, GEDA's schematic editor. I will click on GEDA schematic editor. You will see that the schematic editor window opens. It has light BG because we have configured it for that. Expanding the window. So this is how it looks like. Now on the top title bar, you will see that it is untitled 1.sch. .sch is this extension. Now let us give this a name. We will save. So let us save it in work directory, which we have created for the purpose, and I will call it as example 3. So this name here appears, and we will now fill in this space here with circuits. First, let us pick the components. Now let us see how we add components. The component block here, button here, press that. So you see a dialog box coming up here. It gives you the list of categories of components that are available in the library. Basic devices, connectors, diodes, input output, power rails, radio elements, switches, so on and so forth. Some important things that you need to know: in the power rails, you have to, this is one important thing that you will need, and you will need the ground. This is the reference ground, which will be needed in almost all simulations. Then you will also need from the SPICE simulation include directive. So this is also something that you will need. I'll place it here, all outside. And the various components. So you have the various components of the battery, capacitor, resistor. This can be drawn from these libraries. The basic library is a very general purpose library, very useful. Most of it you will be drawing from there. The various connectors, especially when you're making PCB, diodes, input output, diodes, different types of diodes, general diode symbol. Let's say we need a diode now. Let us say we'll build a half wave rectifier. Then from the basic, let me choose resistance. There are two types of resistance shapes. This is one wiggly wave shape, resistance shape. The other resistance shape, which is like a box. Both are available. You can choose them appropriately. Then you can pick a voltage source. This is a voltage source. Let's say we pick this voltage source and place it there. So for a half wave rectifier, we have all our components here. Let me close this and let me rearrange this. So I could use ER to rotate, keys ER to rotate. I can click on this, ER to rotate. So you have a rotation, and I will place it in this fashion and accordingly have my circuit. You can use the mouse center wheel, thumb wheel, to zoom in and zoom out, zoom in and zoom out. And now to make the interconnections, you can use the wiring. So let us do the wiring. So you right click to release. That's it, connections are also made. Now let us give the names, numbers to these. So double click on that. Let me call that one as V1. So this is D1, R1, and R2. So I've given names for the devices. You can also rotate, you can place it at a convenient point. I will rotate this and then also place it here. Right, so now we have this. We also have to place the ground node. Without placing the ground node, simulation will not work. That is the reference node or the zero node with respect to which all other nodes are measured. Now R1, we need to give value to R1. So let us do that. I will double click on that. Then I will select value, and to the value I will put some 10 ohms. and to make visible I will say show value only and add. So this has come up here and I will push it in this fashion. Likewise, for this double click, I will pick value, add 10 ohms, show value only. I will add it, and that's it. So we have this. And for the diode here, we'll come back to the diode. We need to give value for this V1. Let us make it as a sine wave. So let me include a value. I will say sine 0 325 is the peak value, 50 hertz 0 0. So this will be the value only, add, right. So this will be the sine input we are giving here. Yes. Next, the diode. So the diode, we would like to remember that we had already created the sub-circuit file. So we will use that sub-circuit file. In the work folder, I have copied ex02.sub into ex03.sub. We are familiar with that. So you see that it has a model file and a sub-circuit which is for the power diode. Now let us say we call the name diode power, which I have copied it from the edt master.subcircuit, which I showed last time, where we downloaded it from the website. So this model we will use in this particular schematic, diode power. So we will link it to diode power. So I will open that value. I will say diode power and I will make it invisible, add, and that's it. So this diode is now linked to diode power, but we have to tell where that diode power is existing. We know that it is existing in that ex03.subcircuit file. So let us do an include directive. I will delete this. Let me now add the include directive, which comes from Spice simulation elements. Go down, Spice include directive, and place it here. Close this and to this file unknown, you give ex03.sub, which we just now created. So that is the file it will refer to, and then in that it will take the value of the model, which is diode power and which is that sub-circuit. Another thing that we need to do is to change this from D1 to XD1 because I am referring to a sub-circuit, and therefore this should have a starting character which is X. So we are now ready. I'll tell you, this is a label which can be interposed anywhere. I will I will mark it as, let us say, B. So this is something that can be used for defining a node name. So now this node is defined as B. So I can use V in brackets B to refer to this voltage at this node. Okay. So we have this. Let us now save it in work as EX03 and done. Okay. One more thing that we need to take care, the device is diode, so therefore by default it will always take D as the first character. So we need to remove that. Click on that, and then you can either leave it empty or you can type in sub circuit. Close that and save. That's it. So now we need to convert this circuit into a netlist. So we have to do that in the command line. Let us go to the command line by opening a terminal window. So in the terminal window, we'll do the following. We first go change directory to the work directory, and this is where all the files are kept, and we will use the following command, which I am going to type in, for converting the schematic editor file to netlist file, which is ASCII. The command is like this: gnetlist -g spice -sdb output -o. Output is ex03.net. .net is the output file. The input file is .schematic. This is the schematic file, which is this specific file here, the graphic file. So when you give this command, it will execute and create the netlist file for you. So if you list the directory, you will see that the netlist file is here created. Let us go to the directory structure here. Yeah, so here in the work directory you have the netlist file that is created. So this netlist file looks something like that. This is auto-generated netlist file. It has copied the subcircuit from our ex03.sub file, and diode power is referenced here, and this is the subcircuit, and if you execute this, it should work. We could probably demonstrate that also. So I have copied the ex02.cir into ex03.cir file, where we are doing a transient analysis. 1 microsecond step time, 100 millisecond is the end time. They include the netlist of ex03, which was just generated here, and control commands like usual. Within the .control.nc statement, you have the set background as white, set foreground as black, run the plot, and plot VB. There is no A node defined, only B node is defined, and this is save it. So let us do that. We go to the command line. I will say ngspice ex03.cir, and you have the execution here. So this is the output, which is at this point VB. That's what is VB here. we have defined that node, and the voltage at that point, there is a 50% attenuation and there is rectification due to this diode, and that's what you see here. We have given 325 as the peak. Half of that is the peak that will appear at node VB. So this is just to demonstrate the process of creating a graphical circuit using the Gschem schematic editor, and later convert the graphical file .sch file into a netlist file, an ASCII netlist file, and that netlist file will be called by the .car file as usual, and pass it on to ngSpice for running in the ngSpice environment. So that is what we saw here, and this process is also equally popular among the people while simulating electric circuits. These symbols that we see here, which is already created by ngSpice and given to you, provided to you, and then there are symbols which will be provided to you by some companies carrying the model of their specific components. And as I said, it is good for you to have generic models developed, which we have placed it in the .sub file. Now we have to relate it to a symbol, and then there are different symbols that I have created, which can be made use of in the circuits. So for example, when you click on the component dialog, when it opens, you see like this: local and the basic devices and so on and so forth. We can make our own library of symbols to come in here also by placing in the symbols directory our custom made symbols. I will show how that is done. I will close this for now, and I will go to the browser, and the browser I will go to the same location of website, which is here, surya.dac.iisc.ac.in/lu. This is the website I'm going, and I'm going to click on the resources, go to the resources page. Then in the simulation, I am taking this particular item, my symbols collection. So I'll click on that. So you have this my single symbols collection. It is a zip file. Download that zip file. So it downloads. So from the downloads folder, copy it onto. So in the downloads folder, you'll see that symbols.zip file comes in, and when you extract it here, so within that, so you have 4 more folders containing various symbols, component symbols. So this, if I place it into the GAF folder, which I have done that for you, it will be placed within like this. So now that I have placed it within the symbols folder, if I open Gschem schematic editor, these names will appear. I have prepended everything with A so that it is alphabetic, therefore it will pop up at the top, very top. So let me go to Gschem editor, schematic editor, and I will open that. So when you open it and I go to the component dialog box, now you see that it pops up here right at the top: blocks, bond graphs, components, and some models. So if these are various blocks which have their own sub-circuit models, and these are linked through this schematic. And likewise for the components, different various generic components which I have here, and gyrator. So like that you can pull them and then place it like any other circuit component and then use it to build your circuit. Of course we will use this later, but just now wanted to tell you that you can download this resource and it is free for you to use. You include it into the symbols folder in the GAF directory and you are ready to go while you are selecting the components.